Welcome to week 2. This week we're shifting from using databases to designing them. By the end of this week, you should be able to first understand the purpose and components of entity relationship modeling. ER stands for entity relationship, and it's the foundational technique for database design. Second, learn to identify entities, attributes, and relationships. These are the building blocks. Entities are the things we store data about. Attributes describe those things. Relationships show how they connect. Third, distinguish between different cardinality types. Cardinality answers the question, how many? How many visits can a patient have? How many patients can a provider see? These decisions fundamentally shape your database structure. Fourth, apply entity relationship modeling to healthcare scenarios. We're not learning this in the abstract. We're actually applying it directly to the xHealth database that you'll be working with. And fifth, we'll introduce 2 more healthcare coding systems, LOINC for the laboratory tests and NDC for medications. These complete the picture we started in week 1 with the ICD-10 codes, CPT, and SNOMED CT. Let's quickly recall what we covered last week. We established that a database management system, a DBMS, provides structure, security, and integrity for healthcare data. It's not just a spreadsheet. It enforces rules, manages concurrent access, and maintains relationships between data. Postgres is our tool for this course. It's enterprise grade, open source, and widely used in healthcare settings. We also introduced 3 healthcare coding systems: ICD-10 codes, the diagnosis, what's wrong with the patient; CPT codes, procedures, what was done; and SNOMED CT provides rich clinical terminology for documentation. Now the question becomes, how do we design the database that holds all of this data? How do we decide what tables to create and what columns they should have and how they should connect? That's what ER modeling answers. Let me frame the problem we're solving. Imagine that you're tasked with building a database for a community health center, like our xHealth example. Where do you start? You need to answer several questions. What data do we need to store? Patient names? Sure. Well, what else? Visit dates, diagnoses, lab results, medications, insurance information? And then, how are the different pieces of data related? A patient has visits. A visit has diagnoses. A provider conducts visits. How do we represent these connections? And critically, how do we prevent data duplication and errors? If a patient's address changes, we shouldn't have to update it in 15 different places. If a visit is deleted, what happens to its associated diagnoses? ER modeling answers all of these questions before you write a single line of SQL. It's the blueprint. Just like an architect doesn't start building without plans, a database designer doesn't start creating tables without an entity relationship model. The time you invest in design saves enormous time in development and maintenance. So, what exactly is an ER model? An entity relationship model is a conceptual blueprint for a database design. It was developed by Peter Chen in 1976 and remains the foundation of database design nearly 50 years later. An ER model is a visual representation of 3 things. First, the things we want to store data about. We call these entities: patients, providers, visits, medications. These are all entities. Second, the characteristics of those things. We call these attributes. A patient has a name, a date of birth, an address. These are all attributes of the patient entity. Third, how things relate to each other. We call these relationships. A patient has visits. A provider conducts visits. A visit results in diagnoses. Think of it like an architect's blueprint. Before you pour concrete, and frame walls, you need a plan showing where rooms go, how they connect, where the plumbing runs. An entity relationship diagram serves as the same purpose for the database. You wouldn't build a house without blueprints, so don't build a database without an entity relationship model. Let's start with the first building block, the entities, the things we store. An entity is a distinguishable object or concept about which we store data. Entities can be real-world, tangible things like a patient, a doctor, a hospital, or a medication bottle. But entities also can be conceptual things that don't have a physical form, an appointment, a diagnosis, an insurance policy. The key question is this something that the organization needs to track and store information about? If yes, it's probably an entity. In ER diagrams, entities are represented as rectangles. Simply as that, you draw a rectangle and label it with the entity name. On the screen, you can see a simple rectangle labeled patient. That's an entity. Every patient in the health center serves as an instance of this patient entity. Entities become tables in your database. The patient entity becomes the patient's table. This distinction is important. Entity versus entity instance. The entity, also called an entity type, is the category or template. Patient is an entity. It defines what information we collect about patients in general. An entity instance is a specific occurrence. John Smith, born March 15, 1985, is an entity instance. He's one specific patient. Here's an analogy that helps. Think of a cookie cutter versus individual cookies. The entity is the cookie cutter. It defines the shape. Entity instances are the individual cookies that you cut out. Every cookie has the same basic shape, but each one is distinct. In database terms, this maps directly to tables and rows. The entity becomes the table. Entity instances become the rows in that table. So when I say patient entity, I'm talking about the patient's table and its structure. When I say a patient's instance, I'm talking about one specific row in that table, one patient. How do you identify what entities you need? Well, you start with the scenario. For our X-Health example, what things does the organization need to track? Patients, obviously. We need to store information about the people receiving care. And also providers, the doctors, nurses, nurse practitioners, physician's assistants, the people delivering the care. Visits or encounters, each time a patient comes in, that's a trackable event. Diagnoses, the conditions identified during visits. Medications, what's prescribed to the patients. Lab tests, tests ordered and the results. Insurance coverage, information for billing. Each of these is a candidate entity. Now you might combine some or split others based on your specific requirements. Maybe you need separate entities for doctors and nurses because they have very different attributes. Or maybe you combine them into a single provider entity with a role attribute that distinguishes among them. The process of identifying entities involves understanding the business domain. What does the organization actually need to track? Talk to stakeholders. Review existing forms and reports. Look at what questions the system needs to answer. Now, not all entities are created equal. We distinguish between strong and weak entities. A strong entity can exist independently. It has its own primary key that uniquely identifies it without reference to any other entity. A patient is a strong entity. A patient exists in our system regardless of whether they've had any visits, or any diagnoses, or any prescriptions. We can identify them by patient ID alone. A weak entity depends on another entity for its existence and identification. It cannot be uniquely identified by its own attributes alone. A classic example is the dependent in a human resources system. A dependent, like an employee's child or their health insurance, doesn't exist independently. You identify a dependent by the combination of the employee ID plus dependent name. Without the employee, the dependent record makes no sense. Visually, we can distinguish them in the entity relationship diagram. A strong entity is a single rectangle. A weak entity is a double rectangle, a rectangle inside a rectangle. The relationship connecting a weak entity to its parent is also shown with a double diamond rather than a single diamond. Let me give you a healthcare specific example of a weak entity. Consider vital signs: blood pressure, temperature, heart rate, respiratory rate. A vital sign recording doesn't make sense without context. 120/80 means nothing on its own. Whose blood pressure? When was it taken? Vital signs depend on a visit for context. They're recorded during a specific visit for a specific patient. How would you uniquely identify a vital sign reading? You need the visit ID and a timestamp, plus the vital type. That combination uniquely identifies one measurement. So vital signs is a weak entity. Visit is the strong entity that it depends on. So we call this the identifying entity or the owner entity. In our xHealth database, we actually handle this by including visit ID as a part of the composite key, or by using a surrogate key with a required foreign key to visits. The concept is the same, and this may sound a little complicated, but you'll get this over and over again, and it'll make sense gradually. Now let's talk about attributes, the characteristics that describe our entities. An attribute is a property or characteristic that describes an entity. For our patient entity, what attributes might we have? Well, of course we have to have a patient ID, the unique identifier for each patient. We're probably also going to have a first name and last name. Who is this person? A date of birth, when were they born? Gender, other demographic information. Address, where they live. Phone numbers, emails. Each of these is an attribute of the patient entity. They describe aspects of a patient that we need to track. Now in Chen notation, the original entity relationship format notation, attributes are shown as ovals connected to their entity with lines. You'll see a rectangle for patient with ovals for name, date of birth, address, etc. Now in crow's foot notation, which is more common in industry today, attributes are simply listed inside the entity rectangle, and you'll see a box with patient at the top and a list of the attributes below. Both notations convey the same information, they just visualize it slightly differently. Attributes come in different types, and underlying these types helps you design better databases. A simple or atomic attribute cannot be meaningfully divided further. Date of birth is simple. It's single date value. Social Security number is simple. It's one value. Composite attributes can be broken into smaller parts, like address is a composite that has the city, street, number, zip code. Name might be composite. First name, middle name, last name, suffix. You need to decide, do I store it in one field or in multiple fields? Single-valued attributes have one value per entity instance. A person has one Social Security number, one date of birth. Multi-valued attributes can have multiple values. Phone numbers. There might be multiple values, might have a home phone number, a work phone number, and a mobile number. Allergies can be multi-valued. A patient may have multiple allergies. Derived attributes are calculated from other attributes rather than stored directly. Age is derived. You calculate it from their date of birth and the current date. You could store age, but then you'd have to update it periodically every time their birthday comes around. Instead, you derive it when it's needed. Let's see these visually. In Chen notation, different attribute types have different visual representations. A simple attribute is a plain oval. Date of birth is a simple oval connected to the patient. A composite attribute is an oval with subovals branching from it. Address is as an oval with street, city, state, zip, as smaller ovals connected to it. A multi-valued attribute is a double oval, an oval inside an oval. Phone numbers as a double oval, indicating there can be multiple values. A derived attribute is dashed. Age as a dashed oval, indicating it's calculated rather than stored. In healthcare contexts, examples of simple include the patient ID, date of birth, gender. Data that's composite is address, provider name. Multi-valued includes phone number, allergies, diagnoses. And derived includes age, or length of stay, or their BMI, calculated from their height and weight. Knowing these types help you make design decisions. Do you store age or calculate it? Do you put all phone numbers in one field or separate them? Now let's talk about keys, one of the most important concepts in database design. A primary key is an attribute or combination of attributes that uniquely identifies each entity instance. Every row must have a different value for the primary key. Primary keys have three absolute requirements. First, uniqueness. No two instances can have the same primary key value. If John Smith has patient ID 1001, no other patient can have patient ID 1001. Second, never null. Every instance must have a primary key value. You can't have a patient with no patient ID. And third, stability. Primary keys shouldn't change. If we use patient ID 1001 for John Smith, it should stay 1001 forever. If primary keys were to change, every indirect reference to that record breaks. Examples of primary keys in healthcare, well, patient ID is what we call a surrogate key, a system-generated identifier with no real-world meaning. It's just a number. Social Security number could be a primary key. It's unique, but we currently generally avoid this for two reasons: privacy and the fact that not everyone has a Social Security number. Medical record number is often used. It's assigned by the healthcare organization and unique within that organization. Let's clarify some terminology. A candidate key is any attribute or combination of attributes that could serve as a primary key. It meets all the requirements: unique, not null, stable. A primary key is the candidate key you actually choose to use. For our patient entity, what are the candidate keys? Well, Social Security number is a candidate key. It's unique for each individual. Medical record number is a candidate key. It's unique within the organization. Patient ID is a surrogate key, is a candidate entry. Email might be a candidate entity if every patient must have a unique email. From these candidates, we choose one to be the primary key. For patient, we typically use patient ID, the surrogate key. Why? Because the surrogate key protects protected health information. The ID number 1001 reveals nothing about a specific patient. They're also stable, unlike email addresses that might change. Now, a foreign key is different. A foreign key is the primary key of one entity used in another entity to create a relationship. If visits contains patient ID, then that's a foreign key in the visits table. Foreign keys are how we implement relationships. We'll go into this in more depth later. Healthcare has specific considerations for key design. First and foremost, avoid using protected health information as primary keys. Don't use Social Security number as a primary key. Don't use name plus date of birth. These potentially expose sensitive information. Use surrogate keys, system-generated IDs, whenever possible. Patient ID, visit ID, provider ID, these are just numbers with no inherent meaning. That said, healthcare does have some established natural keys, identifiers that come from the real world. For example, the NPI, the National Provider Identifier for providers. Every healthcare provider in the United States has a unique 10-digit NPI assigned by the Centers for Medicare and Medicaid Services, CMS. If you're storing provider information, you might include NPI as an attribute even though you use a surrogate provider ID as your primary key. NDC, the National Drug Code. Every medication product has an NDC. This is a natural key for medications. LOINC codes for lab tests. LOINC 2345-7 is always glucose in serum or plasma, everywhere in the world. These standard codes aren't necessarily your primary keys, but they're important attributes that enable interoperability. On screen, you can see a table summarizing key choices for common healthcare entities. Patient uses a surrogate patient ID. Provider uses a surrogate provider ID but stores the NPI. Medication uses a surrogate medication ID but stores the NDC, and lab test stores the LOINC code. With entities and attributes covered, let's talk about how entities connect. Relationships. A relationship is an association between two or more entities. It represents how entities interact in the real world. Think about it. Entities don't exist in isolation. Patients schedule appointments. Providers treat patients. Diagnoses are assigned during visits. Medications are prescribed by providers to patients. These verbs, schedules, treats, assigns, prescribes, describe relationships. Examples in healthcare: patient schedules an appointment, provider treats patient, diagnosis is assigned, medication is prescribed. In entity relationship diagrams, relationships are visualized differently depending on this notation. In Chen notation, relationships are shown as diamonds connecting entities. You'll see a diamond labeled schedules between patient and appointment rectangles. In crowsfoot notation, relationships are simply lines connecting entities, sometimes with a verb label on the line. Relationships eventually become foreign keys or junction tables in your actual database. That's the implementation. But at the entity relationship modeling stage, we're just documenting that a connection exists. Relationships have a property called degree, which refers to how many entities participate. A unary or recursive relationship involves one entity related to itself. Example, employee supervises employee. An employee can be a supervisor and an employee can have a supervisor, but both are employees. One entity related to itself. Healthcare example, a provider refers to another provider. One doctor refers a patient. Both are providers. One table, we can handle this with one value. This is the most common type. Probably 90% of relationships you'll encounter. They're called binary relationships involving two entities. The patient has insurance, two distinct entities connected by relationship. Now, a ternary relationship involves three entities. Fortunately, this is less common. For example, the doctor prescribes medicine to the patient. Three entities are involved: the patient, the doctor, and the medicine. The prescription connects all three. Ternary relationships are less common, but are more complex to implement. Often you'll model them as an entity with three binary relationships. Let's look at binary relationships in our X-Health context. Patient to visit. A patient has visits. When a patient comes to the clinic, that's a visit. Visit to diagnosis. A visit results in diagnoses. During a visit, conditions are identified and coded. Provider to visit. A provider conducts visits. Each visit has a provider who saw the patient. Visit to lab order. A visit generates lab orders. The provider orders labs during the visit. A lab order to lab result. A lab order produces results. The lab performs a test and returns the results. Patient to prescription. A patient receives prescriptions. These prescriptions form a web of connections in our database. The entity relationship diagram makes this web visible. On screen, you can see a mini entity relationship diagram showing these connections. Patients connected to visits, visits connected to diagnoses, to lab orders, to providers, lab orders connect to lab results. This visual helps you see the structure before you actually build anything. Here's something that surprises some students. Relationships themselves can have attributes. Consider the prescribes relationship between the provider and medication. Or more accurately, between provider, medication, and patient. It's really ternary. What information is specific to this relationship? Dosage, take 500 milligrams. This isn't an attribute of the medication itself. The medication exists in many dosages, where the patient doesn't have an inherent dosage. It's an attribute of this prescription. Frequency, twice daily. Start date, end date. When does this prescription begin and end? These are attributes belonging to the relationship, not to either entity alone. In the actual database, relationship attributes usually end up in a junction table or an associative entity. The prescription table holds these attributes along with foreign keys to patient, provider, and medication. So when you see a relationship that needs its own attributes, that's often a sign that you need a junction table to implement it properly. Relationships also have participation constraints, rules about whether entities must participate. Total participation means every instance of the entity must participate in the relationship. No exceptions. Example, every visit must have a patient. You can't have a visit without a patient. It makes no sense. If a visit exists, it's connected to exactly one patient. In Chen notation, total participation is shown with a double line connecting the entity to the relationship. Total participation means partial participation means participation is optional. Some instances participate, some don't. Example, a patient may or may not have any visits. A patient can be registered into the system without ever having visited. They exist, but they're not connected to any visits yet. Partial participation is shown with a single line. This matters for database implementation. Total participation often means a not null foreign key. We'll get into that in more depth later. If every visit must have a patient, then patient ID in the visits table cannot be null. Let's apply participation constraints to healthcare scenarios. Total participation examples. Cases where the relationship is mandatory. Every prescription must be linked to a patient. A prescription without a patient is meaningless. Every lab result must be linked to a lab order. Results don't appear out of nowhere. They come from ordered tests. Every diagnosis must be linked to a visit. A diagnosis is assigned during a visit. Partial participation examples. Cases where the relationship is optional. A patient may have 0 allergies. Many patients have no known allergies. A visit may have 0 procedures performed. Not every visit involves a procedure. A patient may have 0 insurance records. Self-pay still exists. These decisions have real implementation consequences. If prescription to patient is total participation, your prescriptions table has patient ID as a not null specification. The database won't let you create a prescription without specifying the patient. If patient allergies is partial participation, a patient record can exist with no entries in the allergies table. It's fine. Think through these constraints carefully. They enforce business rules at the database level. Let's summarize what we've covered with a mapping from entity relationship concepts to database implementations. Entities are represented as rectangles in the ER diagram. They become tables in your database. Attributes are shown as ovals in Chen notification or listed inside the rectangles in crow's foot. They become columns in your tables. Relationships are shown as diamonds in Chen notation or lines in crow's foot. They become foreign keys or junction tables. Primary keys are underlined in many entity relationship diagrams, they become primary key constraints with unique, not null, enforcement. On the screen, you can see a side-by-side comparison of the same mini-model in Chen notation versus crow's feet. Chen uses separate shapes for everything: rectangles, ovals, diamonds. It's explicit and educational, but takes up space. Crowsfoot puts attributes inside entities and uses line endings to show cardinality. It's much more compact, and it's the industry standard. Both convey especially the same information. You should know both, but most tools favor Crowsfoot. Here's an example of the ER diagram for part of our xHealth database. We have 4 entities: the patient with attributes patient ID, first name, last name, date of birth, gender. Then visit with visit ID, patient ID, provider ID, visit date, chief complaint. Provider with provider ID, first name, last name, NPI, specialty. Diagnosis with diagnosis ID, visit ID, ICD-10 code, SNOMED code. The relationships. Patient to visit is a one-to-many. One patient can have many visits. Provider to visit is also one-to-many. One provider can conduct many visits. Visit to diagnosis is one-to-many also. One visit can have multiple diagnoses. This is a basic structure. When we get to part 2C, we'll add lab results with LOINC codes and also add medications with NDC codes to complete this picture. But even this simple diagram tells you a lot about how the database will be structured. You can see where foreign keys will go: patient ID and provider ID and visits, visit ID and diagnoses. So let's summarize the key points from this section. Entities are the things we store data about: patients, visits, providers, diagnoses. They become tables. Attributes describe entities: names, dates, codes, identifiers. They become the columns. Primary keys uniquely identify each instance. Use surrogate keys in healthcare to protect protected health information. Relationships show how entities connect. Patients have visits, visits have diagnoses, so they become foreign keys. Strong entities exist independently. Weak entities depend on other entities for their identification. Participation can be total, must participate, or partial, optional. ER diagrams are blueprints. Design before you build. Coming up next, cardinality and relationship types. We answer the crucial question: how many? How many visits can a patient have? How many providers can treat a patient? These decisions shape your entire database structure. So now we've come to one of the most critical concepts in database design: cardinality. Cardinality. This determines the structure of your tables and where your foreign keys go. Cardinality answers a simple but crucial question: how many? Specifically, cardinality defines the number of instances of one entity that can be associated with instances of another. When we say a patient has visits, cardinality tells us how many visits one patient can have, and conversely, how many patients can one visit belong to. This might seem like a trivial question, but the answer fundamentally shapes your database structure. Cardinality affects the table structure. Do you need a junction table or not? That depends on cardinality. Cardinality affects foreign key placement. Which table holds the foreign key? Cardinality tells you. Cardinality affects query complexity. Joining tables with different cardinality patterns requires different approaches. If you get cardinality wrong, you'll have a database that can't accurately represent your real-world data. You might not be able to store what you need to store, or you'll have a massive data redundancy. So let's get this right. There are 3 fundamental cardinality types that you need to know about. One-to-one, written as one-to-one. One instance of an entity relates exactly to one instance of entity B, and vice versa. A one-to-many is written as a 1:m, or sometimes 1 to n, One instance of an entity A can relate to many instances of entity B, but each instance of B relates to only one of A. And then there's the many-to-many, written as M to N or M to M. One instance of entity A can relate to many instances of entity B, and one instance of entity B can relate to many instances of entity A. On screen you can see a simple visual icon for each. One-to-one looks like a single line. One-to-many has a fork at one end. Many-to-many has forks at both ends. These three patterns cover virtually every relationship you'll encounter. Master these, and you can model any database. Here's a crucial skill: reading cardinality from both directions. Every binary relationship has two directions. You need to consider both to determine the cardinality type. Let's take patient and visit. First direction: one patient can have how many visits? Many. Think about it. Second direction: one visit belongs to how many patients? Visit is a single encounter. It belongs to a single patient. Combining both directions, one to many, one patient has many visits, we call this a one to M. Always read both directions. It's easy to intuit one direction and assume the other, but don't assume. Think it through explicitly. Let me give you a trick. Turn each direction into a sentence. One entity A can have blankety blank entity B. Then flip it. One entity B can belong to blankety blank entity A. The combination of your two answers gives you the cardinality type. Let's examine each cardinality type in detail, starting with one-to-one. In a one-to-one relationship, one instance of entity A is associated with exactly one instance of entity B, and vice versa. Each A has exactly one B. Each B has exactly one A. One-to-one relationships are relatively rare in practice. When you encounter one, it's worth asking, shouldn't these actually be part of the same table? If every patient has exactly one medical record, and every medical record belongs to exactly one patient, why not just manage them in a single patient table that includes all of the medical record information? Often, one-to-one relationships indicate that two entities could be combined, but not always. There are sometimes valid reasons to keep them separate, which we'll discuss later. Visually, a one-to-one relationship shows a single line, or 1, on both ends of the relationship line. In crow's foot notation, you'll see vertical bars on both ends. Where do we actually see one-to-one relationships in healthcare? Well, a patient to medical record number. In theory, one patient has one medical record number, and one medical record number identifies one patient. I say that in theory because, in reality, duplicate medical record numbers in patients with multiple medical record numbers due to mergers are a huge data quality problem. But conceptually, it's one-to-one. Provider to NPI registration. One provider has one national provider identifier. One NPI belongs to one provider. The NPI system was designed this way. Each provider gets exactly one NPI for their career. Employees to parking permit. If your hospital assigns one parking permit per employee, and each permit goes to one employee, that's one-to-one. And patient-to-patient portal account. One patient has one portal login. One login belongs to one patient. Notice these are often cases where we're linking an entity or some kind of unique identifier or account. The identifier only makes sense in the context of that one entity. One-to-one relationships are rare and often suggest merging the entities. When should you actually use them? Well, in situations where security and access control are important. You might separate highly sensitive data into its own table, patient demographics in one table, patient social security number, and patient financial information in a separate table, as the same patient ID number has a one-to-one relationship, but now you can apply different access controls and security and privacy to the different tables, even though they're all being accessed through the same patient ID. Also, when you have optional data that's rarely used, if only 5% of patients have a particular set of attributes, say a research study enrollment details, you might put them in a separate table rather than including them in the other 95% of your rows, and that will keep your records smaller and more efficient to manage and to operate. Different access patterns. Some data is accessed constantly and some is accessed rarely. Separating them can improve system performance. Your main patient table stays lean and fast. The rarely accessed details live elsewhere. And historical reasons. Sometimes systems evolve and what was once a separate system gets integrated. You end up with a one-to-one relationship for historical or political reasons, even if pure design would have merged them. In healthcare specifically, separating protected health information from non-PHI data is a common reason for one-to-one splits. Your core clinical tables might be accessible to many staff, while the tables containing SSN, full address, and insurance details might have restricted access. How do you actually implement a one-to-one relationship in SQL? Well, option 1, merge into a single table. If the entities are always accessed together and there's no security or performance reason to separate them, just make one table. Patient and patient details become one patient table with all of the attributes. Option 2, a shared primary key. Both tables use the same primary key. The patient table has patient ID as the primary key. The patient protected health information table also has patient ID as its primary key and is simultaneously a foreign key referencing patient. They share that key. Option 3, foreign key with unique constraint. One table has a foreign key to the other, and that foreign key has a unique constraint. The patient portal account table has a patient ID as a foreign key, and we add a unique constraint so that no patient can have two accounts. On screen you can see SQL examples for each approach. The shared primary key approach is elegant. It enforces the one-to-one constraint at the key level. The foreign key with unique constraint is more flexible. If you need separate surrogate keys, this is sometimes utilized. For most one-to-one healthcare scenarios, I'd recommend the shared primary key approach because it's clean and easy to enforce. Now let's talk about the workhorse of database relationships, the one-to-many. In a one-to-many relationship, one instance of entity A can be associated with many instances of entity B, but each instance of B is associated with only one instance of A. One patient can have many visits, but each visit belongs to just one patient. One provider can have many appointments, but each appointment has just one provider. One department can have many employees, but each employee in this model works in just one department. This is by far the most common relationship type. If I had to guess, I'd say 80% of relationships in a typical database are one-to-many. Visually, you'll see a 1, a single line on one end, and an M, or a crow's foot, on the other end of that line. The crow's foot, that three-pronged fork, indicates the many side of the relationship. Let's look at healthcare examples of one-to-many relationships. Patient to visit. We've discussed this one. One patient can have many visits over their lifetime. Annual checkups, sick visits, follow-ups, emergency visits. Each visit belongs to exactly one patient, so it's a one-to-many relationship. Provider to appointment. One provider, let's say Dr. Smith, can have many appointments. She might see 20 patients a day, 5 days a week, hundreds of appointments per month. But each appointment is with one provider. And you book with Dr. Smith, it's Dr. Smith, not some random doctor. So it's a one-to-many relationship. Department to employee. One department, cardiology for example, has many employees, physicians, nurses, technicians, administrative staff. In a single model, each employee belongs to one department. One-to-many. Now you might object, what if a nurse works in multiple departments? Good question. Then it's not one-to-many, it's a many-to-many. and the cardinality depends on your business rules. But for now, let's assume one department per employee. It keeps it simple. More one-to-many examples from healthcare. How about visit to diagnosis? One visit can result in multiple diagnoses. Patient comes in feeling unwell. The doctor identifies type 2 diabetes, hypertension, and hyperlipidemia, all in the same visit. 3 diagnoses, 1 visit. But each diagnosis record is linked to one specific visit, a one-to-many. Visit to lab order. One visit can generate multiple lab orders. The doctor orders a CBC, a metabolic panel, and a lipid panel. 3 orders from one visit, but each order originated from that visit. One-to-many. Prescription to refill. One prescription can have many refills. Your blood pressure medication prescription might have 6 refills over the course of a year. But each refill is for one specific prescription, so you have a one-to-many relationship. Insurance plan to patient. One insurance plan, say Blue Cross Blue Shield PPO, can cover many patients, but if we're modeling it simply, each patient has one primary insurance plan. Again, one-to-many. Actually, that last one is debatable. Many patients have primary and secondary insurance, so in a more complete model, patient to insurance might be a many-to-many. Again, cardinality depends on your requirements and your implementation. So how do you implement one-to-many relationships? Well, this is actually fairly straightforward. The foreign key goes on the many side of the table. Think about it logically. If one patient has many visits, where do you put the patient reference? Not in the patient's table. You'd need multiple columns for multiple visits. You don't need to know how many visits a patient will have. Instead, the visits table has a patient ID column, and each visit row says, I belong to patient 1001. Since a visit belongs to exactly one patient, we only need one patient ID per visit row. Let me show this concretely. The patients table has patient ID as its primary key. The visits table has visit ID as its primary key, and the patient ID as a foreign key, referencing the patient. The diagnosis table has diagnosis ID as its primary key, and visit ID as a foreign key, referencing the visit. Foreign keys always go on the many side. The many side table holds references to the one side. This is a fundamental pattern. If you remember nothing else about implementation, remember in one-to-many, the foreign key goes on the many side. Let's visualize this with our X-Health database. On screen, you can see an entity relationship diagram using crow's feet notation. Patients connect to visits with a one-to-many relationship. The crow's foot is on the visit side. The visits table has patient ID as the foreign key. Visits connects to diagnosis with a one-to-many relationship. The crow's foot is on the diagnosis side. The diagnosis table has a visit ID as a foreign key, and visits connects to the lab orders with a one-to-many relationship. The crow's foot is on the lab orders side. The lab orders table has visit ID as a foreign key. So you can trace the foreign key placement directly from the diagram. Whenever you see the crow's foot, the many side, that's where the foreign key column lives. This is why entity relationship diagrams are so valuable. They tell you exactly how to structure your tables before you write any SQL. The diagram is the blueprint. You can read directly into create table statements. Now for the most complex of the three, the many-to-many relationships. In a many-to-many relationship, one instance of entity A can relate to many instances of entity B, and one instance of entity B can relate to many instances of entity A. It goes both ways. One patient can see many providers, their primary care physician, a cardiologist, a physical therapist, a surgeon, and one provider can treat many patients. Dr. Smith might have thousands of patients in her panel. Both directions are many. That's many-to-many. And here's the critical point. You cannot directly implement a many-to-many relationship with just 2 tables. Now, that's a very important concept. Think about that. There's no place to put the foreign key. If you put provider ID in the patients table, you can only store one provider per patient, but patients see multiple providers. If you put patient ID in the providers table, you can only store one patient per provider, but providers treat multiple patients. Neither works. You need a third table. Where do we see many-to-many relationships in healthcare? Well, patient to provider. As mentioned, one patient can see many providers over time. One provider treats many patients, many-to-many. Patient to medication. One patient might take 5, 10, even 15 medications for various conditions. And one medication, metformin, for instance, is prescribed to thousands or millions of patients. Clearly a many-to-many relationship. Provider to specialty. This is interesting. One provider might have multiple specialties. A physician might be board certified in both internal medicine and geriatrics. And one specialty, cardiology, includes many providers, many-to-many. Student to course. A classic example from academia. One student takes many courses. One course has many students. A many-to-many relationship. And finally, patient to allergy. One patient can have multiple allergies, and one allergen, like penicillin, for instance, can affect many patients. So you have a many-to-many relationship. When you identify a many-to-many relationship, immediately think, I'm going to need a junction table. The solution to many is a junction table. This goes by many names: associative entity, bridge table, linking table, cross-reference table, join table. All the same concept. A junction table sits between the two entities and contains foreign keys to both. Let's take the patient and provider. Instead of trying to directly connect patients and providers, we create a third table, the patient to provider table. This patient-provider table has two foreign keys, the patient ID referencing the patients and provider ID referencing the providers. Each row in the patient-provider table represents one relationship instance. Patient 101 is treated by provider 501. Patient 101 is also treated by provider 502. Patient 102 is treated by provider 501. Now, one patient can have many rows in the patient-provider table, linking them to many providers, and one provider can have many rows in this table, linking them to many patients. The many-to-many is decomposed into two one-to-many relationships: patients 1 to patient-provider many, or provider 1 to patients provider many. So on the screen you can see this visually. Patient connects to patient-provider with a crow's foot on the junction side. Provider connects to patient-provider with a crow's foot on its junction side. Let's look at the structure in more detail. Here you see the patient ID as a primary key, the first name, date of birth. The providers table has a provider ID as a primary key, name and NPI number. The patient-provider junction table is going to have the patient ID as a foreign key to patients and the provider ID as a foreign key to providers, and the relationship type like primary care specialists, what have you, and a start date and end date. So what's the primary key of the patient-provider? Well, you have options. You can have a composite key, primary key. This combination of the patient ID and the provider ID becomes a primary key. This means a patient can only have one record per provider, which might be what you want. The option 2 is to have a surrogate primary key. Add a patient-provider ID column as the primary key. Now the same patient-provider pair can have multiple records, useful if the patient stops seeing a provider and then starts again. The choice depends on your business rules. For many healthcare scenarios, the surrogate key with separate unique constraints offers just a little bit more flexibility. Now here's where the junction tables become really powerful: relationship attributes. Consider prescriptions. It's really a many-to-many relationship between patients and medications. One patient takes many medications. One medication is taken by many patients. But prescription isn't just patient X takes medication Y. It has its own detailed data. What dosage? What frequency? What start date? When is it supposed to end, terminate? Who prescribed it? This information doesn't belong to the patient. Patients don't have an inherent dosage. It doesn't belong to the medication. Metformin doesn't have one frequency. It belongs to the relationship. This specific prescription for this patient for this medication. The junction table holds these relationship attributes. The prescription table becomes prescription ID as the primary key, patient ID as a foreign key, medication ID as a foreign key, and provider ID as a foreign key. The dosage, frequency, route, start date, and stop date are all data elements, columns in this table. The junction table has become a full-fledged entity in its own right. This is common. Many-to-many relationships with attributes often get their own meaningful name. It's not just patient medication. Now it's prescriptions. Let's look at the many-to-many relationship in X-Health. Patients to medications via prescriptions. The prescription table links patients to medications with attributes like dosage, frequency, start date, and includes the prescribing provider. Patients to insurance plans via patient insurance. Patient can have multiple insurance plans, primary and secondary coverage. An insurance plan covers many patients. The junction table, patient to insurance, might include attributes like coverage type, effective date, termination date, policy number, etc. And providers to specialties via provider specialty table. A provider can have multiple board certifications. A specialty includes many providers. The junction table might include certification date, expiration date, certifying body, etc. So on screen you can see these three relationships visualized. Each shows two entities connected through a junction table with crow's feet on the junction side of each relationship. When you see this pattern, crow's feet, pointing at a middle table from both sides, you know that it's a many-to-many implemented through the junction table. Now let's talk about how we visually represent cardinality. There are different notation systems, and you should know about the two most common, the Chen and the crow's foot that we've been talking about all day. Chen notation is the original entity relationship notation developed by Peter Chen back in 1976, the same paper that introduced the entity relationship model itself. The Chen notation uses distinct shapes for each component: rectangles for entities, diamonds for relationships, ovals for attributes, and lines for connecting everything. Cardinality is shown as the numbers at the base of the connecting lines, 1 for one, n for, or m for many. Chen notation is explicit and educational. Everything has its own shape, so it's easy to identify what's what. This makes it excellent for teaching and for conceptual modeling, where you want maximum clarity. The downside is space. With separate ovals for every attribute and diamonds for every relationship, diagrams get large quickly. A complex database in Chen notation can sprawl across multiple pages. You'll often see Chen notation in textbooks and academic settings. It's the proper way to draw ER diagrams if you're learning the theory. In Chen notation, cardinality is shown with simple labels. One means one and only one. If you see a 1 near an entity in a relationship, each instance of that entity refers to exactly one instance of the other. N or M means many, one or more, potentially unlimited. Different letters are used when you have many-to-many to distinguish the two sides. Let's see some examples. For a one-to-one relationship, you see one on both ends: patient, medical record. For a one-to-many relationship, you see one on one end and n on the other, such as patient to visit. One patient, many visits. For a many-to-many relationship, you see m on one end, n on the other, patient to provider, but many patients, many providers. Participation constraints. Whether the relationship is mandatory or optional are shown with the line style. A double line means total participation, mandatory. A single line means partial participation, it's optional. So if every visit must have a patient, you'll see a double line between visit and the has relationship on the visit side. Crow's foot notation, also called IE notation for information engineering, is the industry standard rather than Chen. Developed around the same time, it was popularized by consultants at the folks who ended up becoming Oracle. It's what you'll see in most professional database design tools. Crow's foot is more compact than Chen. Entities are rectangles, but attributes are listed inside the rectangle rather than as separate ovals. Relationships are lines connecting entities. There are no diamonds. Cardinality is shown with symbols at the line's ends. The name crow's foot comes from the symbol for the many. It looks like a bird's foot with 3 toes spreading out. Because it's compact, crow's foot scales better to complex databases. You can fit more on a page and still read it clearly. For this course, iText 770, I want you to be familiar with both notations, but we'll use crow's foot for assignments and our documentation. Let's decode the crow's foot symbols. There are 4, built from 2 components. The symbols combine 2 pieces of information. The minimum cardinality must there be at least 1, a 0 allowed, or 1 required. Or maximum cardinality. Can there be more than 1? 1 to max, or many? The symbol has 2 parts, an inner part, closer to the entity, showing the minimum, and the outer part showing the maximum. The 2 vertical lines, 1 and only 1, minimum 1, maximum 1, and the mandatory single. Circle and line, the O with a vertical bar, 0 or 1, minimum 0, maximum 1, optional single. Line and crow's foot has the vertical bar and a less than sign, 1 or many, minimum 1, required, maximum many, mandatory multiple. The circle and crow's foot, the O and a less than sign, 0 or many, minimum 0, maximum many, optional multiple. So the crow's foot, that 3-pronged fork, always means many. The circle means 0 is allowed. The vertical bar means exactly 1, or at least 1. On screen you can see all 4 symbols with their meanings. Study them until you can read them instantly. Let's look at the crow's foot examples. The patient to visit. What symbology do we see there? We see the double bar, then you see the line, then you see the 0 and the less than sign. Reading this on the patient side, you see 2 vertical bars means 1 and only 1. Each visit has exactly 1 patient. Reading the visit side, you got that circle and crow's foot means 0 or many. The patient can have 0 visits, they may have just registered recently, or many visits. And the translation is 1 patient can have 0 or many visits. Each visit belongs to exactly 1 patient. This is clearly a 1 to many. With optional participation, it's not mandatory. Let's look secondly at the visit to diagnosis example. You got the double vertical bar, you got the line, then instead of having the 0 and the less than sign, you have a 1. So this means that it's mandatory. Other than that, it's the same as the other. And the third one, the patient to provider, you have the greater than and less than on both sides and a 0. So this is the many to many through junction. Both sides are optional. So it says that you don't have to have any patients, you don't have to have any providers. But if you can have more than 1, it can be a many to many. So this is the most complex case. In practice, this will be shown with the junction table in between, but the principle is the same. Well, let's put these side by side and see what happens. On screen, you can see the same relationship, patient to visit, 1 to many, in both notations. The Chen notation shows the patient as a rectangle, the visit as a rectangle, and the has as a diamond between them. There's a 1 near the patient and an N near the visit. Patient attributes such as are as ovals, the patient ID, the patient's name and date of birth. The visit attributes are as ovals. In the crow's foot notation, the patient is a rectangle with attributes listed inside. The visit is a rectangle with attributes listed inside. And then there's a line connecting them with the vertical bars on the patient side and the crow's foot on the visit side where it's one to many. Same information, different visualization. We need to learn both. When do you use which? You use the Chen notation when you're learning ER modeling for the very first time. It's more formal. If you're creating a high-level conceptual diagrams for non-technical stakeholders, or if you need to show every detail explicitly for documentation. If you're in an academic setting where Chen is expected. On the other hand, you use crow's foot notation when you're designing for actual implementation. It's more pragmatic, more practical, and especially if you're using industry database design tools. You'll need compact diagrams that fit on one page. You're working with developers and database administrators who will expect it, and you're doing professional database consulting work. Most modern tools support crow's foot. For iTech 770, I want you to understand both, and you should be able to read a Chen diagram if you encounter one, but for your assignments and the X-Health database documentation, we're going to be using crow's foot. All right, let's formalize what we've been discussing intuitively. Cardinality has two components, the minimum and maximum. The minimum cardinality, also called optionality, answers, must there be at least one related instance? Minimum 0, optional, a patient may have 0 visits, it's allowed. Minimum 1, mandatory, every visit must have at least one diagnosis, it's required. Maximum cardinality answers, can there be more than one related instance? Maximum 1, at most 1. A visit has at most one patient, exactly one in fact. Maximum n, for many, unlimited. A patient can have any number of visits. You'll sometimes see cardinality written as minimum maximum pairs, 0, 1, optional, single, 0 or 1. 1 to 1, mandatory single, exactly 1. 0 to n, optional, 0 all the way up. Or 1 to n, 1 is mandatory, but you can have as many. So in crow's foot notation, the inner symbol closer to the entity represents the minimum, the outer symbol the maximum. Cardinality decisions aren't just technical, they encode business rules. Let me give you some examples. Design question. Should a visit require at least one diagnosis? If yes, every visit must have at least one diagnosis. Then the minimum cardinality from visit to diagnosis is 1. If no, a visit can exist without a diagnosis, perhaps for canceled visits or incomplete documentation, then the minimum is 0. Notation O, 0. Optional. What's the right answer? Well, it depends on the organization's business rules. Some clinics require a diagnosis for billing. Some allow visits without a diagnosis for certain encounter types. Design questions. Can a patient exist without any visits? Oh, yes. A patient can register into the system before they have their first appointment, so their minimum then is 0. If no, you can only create a patient record when they actually visit, then the minimum is 1. Most healthcare systems allow patients to exist without visits. These decisions have real implementation consequences. Minimum 1 often translates to not null foreign keys and check constraints. Minimum 0 allows nulls. Document your cardinality decisions and the business rules behind them. All right, we're coming to the end. Let's talk about this part 2B takeaways. What is cardinality and the relationship types? Cardinality defines how many in the relationship. It shapes your entire database structure. The 3 main types are 1 to 1, 1 to many, and many to many. Junction tables resolve the many to many relationships and hold the relationship data and attributes. Chen notation uses rectangles, diamonds, ovals, and 1NM labels, and it's good for learning and conceptual models. Crow's foot notation is compact, uses symbols, online endings, and is the industry standard. Use it as you're implementing. Minimum and maximum cardinality, encode business rules without optional versus mandatory relationships. So this finishes this. We will next go on to two more of our ontogenies, our vocabularies. We'll be talking about LOINC and NDC. LOINC is for laboratory, NDC for medications. We've already talked about the diagnosis, the ICD-10, the SNOMED, and the CPT codes. And this will round out the other two coding vocabularies that we'll be using in our databases. Look forward to talking to you soon.